Hello guys, now we get back to this class to work with the Vapnik-Chervonex dimension. The Vapnik-Chervonex dimension is a capacity measure. It tells us basically what is the greatest sample size that can be classified in every possible ways. For example, let's start with the definition. So if I have some bias, some algorithm bias, and let's suppose we have some sample size, like with I don't know, with 3 examples, only 3 examples. And let's suppose that those 3 examples, of course, belonging to the integers or positive integers, I can define the number of possible functions inside my bias. This is the bias again of my algorithm. And this is the sample size I had access to. And this sample, this particular sample with my algorithm bias, can indeed provide a cardinality. This means the number of functions provided by my classification algorithm is equals to 2 power to n. When we say 2 power to n over here, we are talking about a single hyperplane being capable of dividing space in 2 regions. So if I have, for example, just one hyperplane, this holds. But if I have more hyperplanes, there are some modifications we need to come up with over here. This maximum number of instances, of examples that can be classified in every possible ways tells me a lot about the capacity of an algorithm bias, what is referred to the Vapnik-Chervonex dimension. Just to have an idea, let's start with a simple example. Here we have 3 points on a bidimensional plane, on a 2-dimensional plane. If I just define my hyperplane over here like this, and I consider every point to be negative, I could define it like this and consider every point to be positive. I could define cutting over here and having 1 positive, 2 negatives, or the opposite, 2 positives, 1 negative. That's the case, that's the number of possibilities that I have for this collinear sample. When we talk about the Vapnik-Chervonex dimension, we are talking about the worst case scenario. But let's consider that in the worst case scenario, our sample is not collinear. Our 3-point sample can assume something that we call the general configuration or general setting, as mentioned in mathematics. The general position setting or general position configuration is the one in which no 3 points are collinear to each other, so they have some perturbation. Assuming those perturbations in a single hyperplane, I can still come up with 8 possible ways of classifying these 3 points. That's the greatest number for 3 points on a plane. If I can use a single hyperplane and come up with 8 possibilities, I can cut, I can shatter, I can divide this sample in every possible way. So my Vapnik-Chervonex dimension for a plane with 3 points in general point configuration is at least equals to 3, meaning that a 3-sized sample can be shattered or classified in all possible ways. But what happens if I come up with an additional element in my space, one additional point? If I try to shatter or classify in every possible way using a single hyperplane, instead of having 2 powered to 4, which would be 16, I have 14 possibilities. Why 14 possibilities? because it's just impossible to come up with these other two classifications having a single hyperplane. Why? Because if I have a single hyperplane like this, it's impossible to cut over here as it would be possible having a second hyperplane and defining, for example, this element as negative and this as negative, and both inside those two hyperplanes as positive, or the opposite, which would be positive, positive, negative, negative. So the lesson we can get from that is that the Vapnik-Chervonex dimension for a plane, our input space defined in terms of a two-dimensional plane, is capable of cutting in every possible ways just a sample size with 3 elements if we have a single hyperplane. If we have more than a single hyperplane, it's going to be different, of course. But having a single hyperplane, that's the limit. That limit tells us something quite interesting, which is this. For example, if the Vapnik-Chervonex dimension for a given space of admissible functions is 3, and for another space of admissible functions, let's call it like F2, is going to be 5, this means I can classify in all possible ways a 3-sized sample and here a 5-sized sample. In this situation, I will have less possibilities for classification. Here we have more. But there is a problem, and I suppose you guys remember, the greater my Vapnik-Chervonex dimension is, the greater is also the possibility or the probability of having the memory-based function inside my bias. Why that's the case? Let me see. I think I had something over here. Let's see. Yeah, I can draw. I can draw over here. You can open like some open office over here. Oh yeah, could be this one. Yeah, I suppose it is. Let's see. Is this a draw? Let's see. Yeah, let's see. Okay. So I'm going to draw for you guys. Let's suppose this is the universe containing every possible function in the universe. And here we have some algorithm biases. First algorithm bias could be this one. Let's bring it to here. Let's use a different color. Be like, I don't know, any color, like yellow, yeah. And here we have another more restricted space of admissible functions, aka bias, algorithm bias. This one's going to be like green. Okay, let's suppose this is a space of admissible functions whose Vapnik-Chervonex dimension is equals to 3 and this is equals to 5. What basically means is that this one has less possibilities, less functions to select from the bias to come up with a good solution. And this has more functions. By having more functions, of course, the probability of containing a memory-based classifier over here is greater than here. That basically means that I will need a greater sample size to train this classification algorithm rather than this classification algorithm that provides a more restricted bias. I suggest you guys to read, again, I mentioned that before, but to read this paper, Statistical Learning Theory, Models, Concepts, and Results by von Luxburg and Shokov, to understand the big picture behind this. Then we'll discuss more along the following classes, of course. Just to bring another point, another important theoretical definition. If I have points in a given input space Rn, the hyperplane, a single hyperplane shattering or cutting or classifying this space will be an object of n minus 1 dimensions. So if I am working on R2, my hyperplane is going to be a line. This means it is going to be 2 minus 1. It's going to be a one-dimensional object. That's simple, of course. And the VC dimension is going to be always the number of dimensions I have in my input space plus 1. That for a single hyperplane. So if I'm working on R5 with a single hyperplane, my hyperplane will have 4 dimensions, and my Vapnik-Chervonex dimension will have 5 plus 1. It will be 6, my Vapnik-Chervonex dimension. That means I can shatter, I can divide a 6-sized sample in every possible way, having a single hyperplane that divides my space in positive 1 and negative 1. Of course, if I have more possibilities, more classes, this changes. But let's start with what is basic rather than going to a very complex example, of course. So this is the foundation behind the shattering the Vapnik-Chervonex dimension. There is another important subject to mention. I don't know if you guys remember, but if I consider the shattering coefficient, I will have something like this. For a sample with n examples, how many different classifications I can come up with? If I have a single hyperplane in 2 dimensions in a space R2 with a single hyperplane, I will have something like this. For a single point, I will be capable of coming up with 2 powered to 1 classifications, 2 classifications. If my sample size is 2, I will be able to build up 4 classifications. If my sample size is 3, as you guys have seen, I will be able to come up with 8 different classifications. If my n is 4, by the way, fortunately, I will not be able to produce 2 powered to 4. I will not be able to produce this. Actually, instead of producing 16, I will produce less. I will produce 14. If I use 5, I will not produce 2 powered to 5, which is 32. Instead of 32, I will produce 22. You know what's interesting about this? This scenario in which I have the sample whose size can be classified in every possible way, and this is the greatest sample. This defines my Vapnik-Chervonex dimension for my algorithm bias to be equal to the sample whose size can be classified in every possible way, which is 3. From here, you guys notice our complexity in terms of the number of classification, which is exponential up to here, starts being polynomial afterwards. That point is the point that the complexity of our shattering coefficient starts becoming polynomial. Remember that if it is polynomial, what can I do with that term delta equals to 2 times the shattering coefficient for a 2-size sample multiplied by the exponential of minus my sample size times epsilon to the square, oh that's funny, divided by 4. What can I do with this? Of course, again, if this is polynomial, what I can do is to come up with this formulation. Exponential of log of my shattering coefficient function, again, okay, minus this term over here. what is really interesting. Why? Because now I can understand that if this guy is written in a polynomial form, for example, n power to p, given p is a constant. What can I do? I can just rewrite this as n powered to p. And given the property of logs, I can use p times log of n. And of course, something that's a log of n in positive terms and something that's negative simply in terms of n, I mean, it's linear, and this is log. Of course, this negative term is going to dominate our process, and it's going to converge to zero because this whole exponential is going to be negative. It's going to be an exponential of some negative term over here. 2 times the exponential of some negative term. Given this term is negative, this exponential is going to approach zero. And by approaching zero, my delta, which is an upper bound for our probability, is going to tell me that my empirical risk is a good estimator of my expected risk. That's all for now. We go back in the next class next video just to discuss on the margin bounds. And after discussing on the margin bounds, we're also going to discuss a lot about the scattering coefficient in the next videos. Bye bye, guys.